Hi everyone. In this video you're going to learn about straight line motion, which is also known as linear motion or even particle motion. So first of all, what we mean by straight line motion is that the object is moving along a straight line. That line could be a horizontal line, meaning the object is either moving left or right, or it can be a vertical line, meaning that the particle is moving up or down. Okay, now, first of all, there are three different functions we deal with: position, velocity, and acceleration. And usually the position function is represented by x of t. Sometimes you'll see it written as s of t, but most of the time it's represented as x of t. So if x of t is the position function, then the velocity function is the derivative of position. So x prime of t would equal the velocity function. If we find either the second derivative of position or the first derivative of velocity, then we get acceleration. So it's either the first derivative of velocity or the second derivative of position is acceleration, which is a of t. Okay, an easy way to remember this, I always like to call it PVA. Position, velocity, acceleration. And they're just basically higher order derivatives. Okay? The derivative of position is velocity, the derivative of velocity is acceleration, or also acceleration is the second derivative of position. Okay, now you guys, graphically, we can just relate this to the fun chart. So remember the fun chart, which goes F, F prime, F double prime, and it goes plus, minus, increase, decrease, concave up, concave down, plus, minus, increase, decrease, concave up, concave down, plus, minus, increase, decrease. So instead of the F, F prime, F double prime, just think of it as position, velocity, acceleration, PVA. All right, let's look at some examples. All right, so we're going to start with a graphical example. So in this scenario, Mr. Bean is playing catch with his best friend, which is himself. He throws a tennis ball straight up into the air. The height of the ball is modeled by s of t, so that is also our position function, where t is time in seconds and s is the height of the ball from the ground in meters. Okay, so you guys remember we did this before, where we sketched graphs of derivatives, and then we also practiced matching the graph of a function with its first derivative and second derivative. And remember that we learned that points, which are relative extrema, would also represent a point where the tangent line is horizontal, means that the derivative would equal 0. So it's looking like if this is my position function, then the velocity, which is the derivative of position, I would have an x-intercept where I have this relative maximum, which in this case is also an absolute maximum, but either way, where that maximum is on the parabola, that would translate into an x-intercept for the graph of the derivative. All right, so, just kind of approximating about where that is. It's looking about right there. So over here, I'm just going to mark that as an x-intercept. Maybe. Okay, and then since the position function is increasing, we would know that the derivative would be positive. So the graph of the derivative would be above the x-axis. And then because the position function is decreasing, here it's increasing, then decreasing, we know that the graph of the derivative would be negative or below the x-axis. And remember, we can also think about our power rule. The position function is a quadratic function, so if I find the derivative of it, I'm going to get a linear function. In this case, the linear function would have a negative slope. So think about what would happen for our acceleration function, which is the derivative of velocity. If I'm finding the derivative of a linear function that has a negative slope, then the graph of the derivative is going to be a horizontal line that's going to have a negative value. And it just so happens to be negative 9.8, and I'll show you where I got that from. But anyway, so here would be about what our acceleration graph would look like. Now, don't forget that we were given the equation, so, you know, we could also find these equations algebraically. If this is my position function, then to find the velocity, I would just find the derivative, and I would get negative 9.8t plus 18. And then to find acceleration, I'll just find the derivative again, and I get negative 9.8. So now you can also relate the equations to the graphs of position, velocity, acceleration. Okay. Let's look at this example where we're just given the position function, which is x of t, for t greater than or equal to 0. All right, the first thing we're asked to find is the displacement of the particle during the first 2 seconds. Now, displacement is the distance from the starting point, okay? So to find the starting point, or the position, when t equals 0, we would just find x of 0, plug 0 in to the position function, and we would get 3. And then to find the position after 2 seconds, we'll find x of 2. So we'll plug 2 into x of t, and we actually end up getting negative 5. So to find our displacement, we will subtract negative 5 minus 3, and we'll get negative 8 as the displacement, which I hope that makes sense. Think about a number line. If the particle is at positive 3 at t equals 0, and then is at negative 5 at t equals 2, it has traveled 8 units to the left, okay? And keep in mind that this particle is moving along the x-axis, okay? All right, find the average velocity of the particle during the first 4 seconds. So average velocity would be finding an average rate of change, okay? Which, remember, that is just regular slope formula. So to find the average velocity, we would basically find the slope, which is a rate of change, given the position function. So we would want to find x of 4 minus x of 0 over 4 minus 0. Okay, now, x of 4, plugging 4 into the position function gives us positive 3, minus x of 0, which is also positive 3, over 4 minus 0, would actually give us 0 over 4, which would equal 0. So the average velocity during the first 4 seconds is 0. All that means is if we were to connect the 2 points on this graph, like when x is 4, you know, if we plotted the points 4, 3, and 0, 3, and connected those points with a line, that line would be horizontal, okay, which is why we're getting 0 for the average velocity. Okay, let's look at the next one. Find the instantaneous velocity of the particle when t equals 4. So remember, instantaneous velocity means derivative because you're finding slope at a point. Okay? You're finding the rate of change at a single point. So we will, to find the velocity, we will find the derivative of x of t. Okay, so this is just power rule. So we'll get 3t squared minus 8t, and then we'll just plug in 4. So v of 4 is going to equal 3 times 4 squared minus 8 times 4. So let's see, we'll end up with 4 squared is 16 times 3 is 48 minus 32. So we're going to end up getting 16 for the instantaneous velocity when t equals 4. Okay, find the acceleration of the particle when t equals 4. Well, that's easy. To find acceleration, we'll find the derivative of velocity, which is going to equal 6t minus 8. And then we'll plug in a 4, and we'll get 6 times 4 minus 8. So we'll end up with 24 minus 8. And that will end up giving us 16. Okay, moving on. Let's look at an example where we're given a graph. Now, this time the graph is the velocity function, okay? So you guys, this is no different than when we were analyzing a function based on the graph of its derivative, okay? So this is definitely fun chart. Okay, when does the particle move right? Well, keep in mind that velocity is positive or negative, and the sign tells you the direction, okay? So we would know that the particle is moving to the right when the velocity is positive. Since we're looking at the velocity graph, we're just looking at where the graph is above the x-axis, okay? So the particle is moving to the right, it looks like on the interval from 0 to 1. And also on the interval from, looks like, I'm having to kind of estimate this x-intercept right here. I'm just going to call it 4.5 to make things easier. 4.5 to 7 is when it's moving to the right. Okay, and then when is it moving left? It's moving left from 1 to 4.5 because velocity is negative on that interval. Okay, let's come back to the speeding up, slowing down. Let's move on to when is the particle's acceleration positive, negative, and 0. Okay, now we would be looking at the derivative. Okay, so, if it's helpful, then draw your fun chart. See if I can squeeze it in here. Positive, negative, increase, decrease, concave up, concave down, positive, negative, increase, decrease, positive, negative. And then remember, we're just relating this to position, velocity, acceleration. So when is acceleration positive? That would be when velocity is increasing. We're looking at the velocity graph. So velocity is increasing from 2 to 6. Okay, when is the particle's acceleration negative? Acceleration would be negative when velocity is decreasing. Okay, so acceleration is negative from 0 to 2 and also from 6 to 7. Okay, now, when is the acceleration 0? Well, acceleration would be 0 whenever, this changes from positive to negative. So that's going to happen when velocity changes from increasing to decreasing or vice versa. Okay, so acceleration would be 0 at x equals 2 and also x equals 6. Okay, when does the particle have the greatest speed? Well, remember that speed is the absolute value of velocity. Okay, so you guys, graphically, when you find the absolute value of a function, any part of that graph that has negative y values, so any part of the graph that's below the x-axis, is going to flip above the x-axis because any negative y values are going to change to positive y values when you find the absolute value. So for instance, this part of the graph is going to flip vertically and will now be above the x-axis. So now, when does the particle have the greatest speed? We're basically just looking for the absolute maximum, and the absolute maximum value is 2, but that's occurring when t equals 0 and also when t equals 2. That's reminding me that I should have used a t here instead of an x. Okay, now let's go back to the whole speeding up, slowing down. So, you guys, to determine speeding up and slowing down, you have to compare the signs of velocity and acceleration. And it works like this. If acceleration and velocity have the same sign, whether both positive or both negative, then the particle is speeding up. If velocity and acceleration have opposite signs, then the particle is slowing down. Okay, so remember, we're looking at the velocity graph, okay? So, to know the sign of velocity, we would just look at this graph as whether it's above the x-axis or below the x-axis, okay? But to know the sign of acceleration, we would be looking at where this graph is increasing or decreasing, okay? So for instance, let me just pick some intervals here. From 0 to 1, your velocity is positive because the graph is above the x-axis, but your acceleration is negative because the graph is decreasing. So from 0 to 1, the graph would be slowing down. Okay, and then I'm going to add speed up. Okay, now let's look at it from 1 to 2. Okay, from 1 to 2, velocity is negative, and acceleration is also negative because the graph is decreasing. So because velocity and acceleration are both negative, the particle would be speeding up from 1 to 2. Okay, now let's look at 2 to what I was estimating to be about 4.5. Okay, velocity is negative, but acceleration is positive because the graph is increasing. So in that case, the particle is slowing down from 2 to approximately 4.5. Okay, let's now go from 4.5 to 4. Velocity is positive. Acceleration is also positive because the graph is increasing. So that means the particle is speeding up from 4.5 to 6. 4.5 to 6. Sorry, this is a little messy. Okay, now from 6 to 7, velocity is positive, acceleration is negative, again because the graph is decreasing. So that means the particle is slowing down from 6 to 7. Okay. Here are some important facts to remember. Suppose an object is moving along a straight line, such as the x-axis, so that its position x as a function of time t on that line is given by y equals x of t. To find the average velocity of the object over the time interval, you would just find the change in position over the change in time. Now, I feel like that's a little confusing. I would just remember it as like x of t sub 2 minus x of t sub 1 all over t sub 2 minus t sub 1. But it is essentially slope formula, okay? Instantaneous velocity of the object is the derivative of the position function with respect to time. So remember, v of t equals x prime of t. Speed is the absolute value of velocity. Acceleration is the derivative of velocity or the second derivative of position. Okay, now here's a few words or phrases that are used often in questions on the AP exam. Initially. Initially means when t equals 0. At rest. At rest means the particle is not moving, which means the velocity function would equal 0. At the origin is describing position, which would mean x of t would equal 0. Okay, velocity is positive, means the particle is either moving right or up. Velocity is negative, means the particle is moving left or down. And then here's another description of the speeding up or slowing down. If the velocity and acceleration have the same sign, both positive or both negative, then speed is increasing, okay? If an object's velocity is negative 40 miles per hour and the object accelerates negative 10 miles per hour, then the object is speeding up. If velocity and acceleration are opposite in sign, meaning one positive and the other negative, then speed is decreasing. Here's an example. If an object's velocity is negative 40 miles per hour and the object accelerates 10 miles per hour, then the object is slowing down. Okay. So you guys, we will definitely do some practice with particle motion because it is one of those topics that shows up a lot on the AP exam. So study some of this, and as always, thank you for watching. Have a good night.